first of all, I'd like to say thank you to the organisers for inviting us to come along. It's a very important conference for us, this one, and it's nice to be invited to talk and present what we do and our side of it, I guess. So I'm going to split this talk into two different parts, and I will wear two different hats during these two different parts of the talk, and I'll swap the slide theme as I do it. So I will show from a PDB-E perspective what we can do with good data, and then I'll show how we get there from a wwPDB perspective. So I guess the important bit to know that all of you have realized here is that the coordinates on themselves don't tell you anything. They're just a set of coordinates. The important bit is adding the biological context to this. It's the bit we do as the archive. So we want to relate them to each other. We want to say what the molecules are, what the chains, what the complexes, the assemblies, and all of this extra metadata that's required so that you can find the things you want. So at PDB-E, given all this lovely metadata that we receive from the PDB, of which we're part of, obviously, we are adding extra context to this structural data. So we're building on top of what's in the PDB archive in our new PDB-E knowledge base resource. So this is adding extra context to structural data. So initially, we focused on proteins, and I'll show you what we've done there. We'll be focusing on binding sites and ligands next, and I'll ask for some help from that later. And then later on, we'll work on complexes, and it will become apparent why as I go through. So how does it work? What do we do here? So we have taken PDB entries that we get from the wwPDB. We add data from additional resources. So other places would have extra metadata that isn't normally findable, and it comes into our database. And then we present this in interconnected PDB entries. What this means is we can flip the entry view to show you aggregated views, which hopefully are more informative and more useful. So for this particular uniprot, so this is looking at our protein page. So this is every structure that has the same uniprot in a particular protein. We've aggregated all those structures together. There are 88 structures, and there are 81 ligands that bind to this particular protein, whether it's in complexes or whether it's on its own. We can tell you what all the publications are. And on the right-hand side here, we can tell you which parts of the uniprot actually we have structures for. And in this example, large parts of it we don't have. If we look at the ligands bit, for example, because it's per uniprot, we can tell you where all these ligands bind, and you can find common binding residues. And then we can group the molecules to show where they're the same. And we can do something similar with interaction sites, with other macromolecules within structures of the PDB, and link this to partner resources to see where things are common. But we can't do that on our own. We need the PDB to do this, and we need your lovely data that we have in the PDB. So how do we get to that point? First of all, who are we? So I've seen a few different slides of showing different parts of the PDB. So together, between BMRB, RCSB, PDB-E, and PDB-J, we are the wwPDB. And we together produce the PDB archive, which is available identically from every one of these sites. And we just put a website on top of it, which differs. One thing I've heard here is the lovely growth of EM, and it has. This is EM over the last few years, number of depositions or number of released depositions we have. That's an exponential growth, it's huge. Started at quite a low level, quite high. Should we put this into a bit of context though, as this is CCP4? Let's add X-ray structures to the same graph. So X-ray are up here. So although EM has become the second experimental technique within the PDB, overtaking NMR a few years ago, now 4 years ago, it has still got a long way to catch up with X-ray, which forms the bulk of depositions that we have within the PDB. For all of those that you are scared that you haven't learnt EM yet. Some of you, maybe. What do we provide as the wwPDB? So we provide the OneDep deposition system. This is common for EMDB, PDB, and NMR data as well. So NMR structures we have as well in there. We have a validation server, so you can validate your structures before you come to deposition. We have a validation API, which you've seen some talks of how it's been used within CCP4 I2 and CCP4 clouds, so that you can pre-validate your structures before you even think about using a validation server and then think about depositing. And all a part of this, we give you our lovely validation reports, which we have these sliders. So we do validate geometry. We don't reject things, but we do validate geometry. So I do like these ones here. We have our lovely toilet seat tryptophan that I do quite like. That's quite good, that. And this one, what happens when you turn off restraints, basically, of this? You get a collapse. Neat ways of storing hydrogens. They look much neater there, to be fair. They take up a lot less space. Note there's no PDB codes on here, so there's no, hopefully, embarrassment from you guys. And that one was fixed before it went live. And this one we've seen in quite a few EM structures recently, which is anti-bumping going a bit mad. So this lysine does go straight through the middle of that phenylalanine. And it's just split it and caused a 4-angstrom bond. So do look at your structures when you refine them. This will be automatic that this will have done this. Please check. We are working to improve the validation report to add more things to it. It isn't a quick process. Some of the guys here that they've presented are much, much quicker at how you do turnover validation. We're a bit slower, but we are improving things. So we've added from the global phasing Buster reports, validation in exactly as they have it in Buster reports. So it's Mogul analysis of small molecules showing geometry outliers and then ligand density fits in there. And when we do the annual recalculation of validation reports, every entry that has ligands over a certain size will have this information. Relevant to a lot of the discussions here, we will shortly be adding EM validation to the validation report. It is not there yet. It is coming very soon, including a load of pictures, which will show you how well things match, how well the model and the coordinate, model and the map match to each other. Sliders here showing per residue analysis of how these things overlap. So all the red spotty bits are where the atoms are not in the volume. So the residues don't fit. And we'll, if you give us half maps, which hopefully everybody will, we can calculate FSEs and compare your resolution with our resolution. And this one's slightly off, so that's the depositor's suggested resolution. The real one will be somewhere a bit further down here. All of this is in OneDep and the validation server, and it pre-tells you major validation issues. So hopefully you get a big chance to spot these things. We tell you about all the usual stuff, bond angles, bond lengths, outliers, clashes, so you have a chance to review before people like me stand up and show your structures. That's geometry validation. That's part of what we do. That doesn't get us to where we were with KB, though. So what we do is the extra bits on top of that. It's the validation of the metadata and the curation that we add on top. So OneDep is driven by the mmCIF dictionary, completely. All of the things that we have in there are driven by the dictionary. So there's a website for the dictionary, which will tell you everything you need to know in there. And the dictionary itself is not maintained, is helped develop by the mmCIF working group, which guide us in development of the dictionary. And any big changes always go through them. So this involves people of the community. It isn't just us. So quite a few members are in this room here. what do we get out of the dictionary? We get regular expressions. You may have made a few while doing depositions. These are different types of regular expressions. So, for example, DOIs will start with a 10. Seems reasonable. We have enumerations, so we force you to only enter pieces of software. So if you're making something new, tell us about it so we can add it to our list. We update this frequently. Boundary conditions, and hopefully you can spot this one's pH going from 0 to 14, but we'll warn you if you give pHs outside 3.5 and 10. So we have flexible boundary conditions. On the form, this looks something like this. So here's our sanity check warnings, which tell you when we expect it within a particular range, but you've not violated it. And then when it comes to things like detectors, it's a drop-down list, so you can't spell Eiger incorrectly. Well, you can try. Yeah, we've had people try. Why do we do that? What happens when we don't? How many different ways can you spell engineered? We had quite a few. I do like ones that we fixed of molecular replacement, which is a very good technique to use. Refined with Refamac, which is probably better at removing hair than refining your structure. pHs of 100 we did have. Believe it or not, we didn't have boundary conditions for pH until relatively recently, although that's quite known and that's wrong. Crystallization temperature of 100 Kelvin, and we've had people stand up on this stage and tell us that we've got these things wrong and they need to fix them. So when we don't have enumerations, we get things wrong as well. I mean, looking at one particular thing, to method to determine structure, good luck if you're going to use this. There are 866 unique values of how you could determine a structure. We are working to clean them up, but it's going to take us a long time. If you do have a restriction, like we have for diffraction source.source, it's a type of thing, synchrotron, a rotating anode, things like that, we only have 10 unique values, much, much more restricted, which means you can now look at it in the PDB and query things. Legacy data causes a lot of headaches. Legacy data was done in PDB format. And for those of you who don't know, PDB format came from punch cards. So when we do mean legacy, we really, really do mean legacy. I guess how much of the audience has seen a punch card before? It's the people at the front have seen it. Those at the back, the students at the back have not seen it. Fair enough. Okay. So this was last updated in 2012. So this is well out of date. CIF is the standard. CIF is what you use. Anybody who's saying PDB files, I hope you mean PDB files from the PDB, but mmCIF. If you're not, you are using stuff that was last updated in 2012 and cannot handle large structures. It is limited to 99,999 atoms and 62 chains because of restriction of the column widths. Move to CIF. Historical data we had from collecting things is very noisy, as I've just shown you, and we have been working to clean this up. I won't go through the list, but lots of things we've done over the last few years, and we do work as a group of annotators very hard to clean up this data so you can use it. For example, I'll highlight we added hard limits for pH, and as has been a focus of a few talks, we are correcting links within the PDB, and we are improving our software so it doesn't get wrong again. And we are listening to you. Just to prove we're listening to you, I added this just earlier. So lice PLP, we do have 35 entries that are missing a linkage, and they have a close contact instead of a link. It's not that simple to fix them though, because I don't know what this is doing here. And we have other bits where we have things a bit strange. So we expect odd things to find when we look at these data. And we've got most of these that are missing links. I didn't show them here, but this geometry here of this ring is not flat and it's been pushed away. So the link is too long. What don't we validate yet? Scaling statistics. And you've seen talks of how we're working with the developers at CCP4, Global Phasing, and Phoenix to automate this so that you guys don't have to enter these things manually, because you make mistakes when you enter things manually. That's perfectly reasonable. So we're we're working, quite hard with that. The other thing we don't validate are earlier metadata, like what detector did you use? We don't know. We don't have a linkage. So, for example, Massive 1 has one detector. Here it is in the image on the website. You guys, as you've entered stuff, have told us it's 14 different detectors. And what can we do? We would find that very hard to restrict. So we need to, what do we need to do? We will parse anything given to us in an mmCIF file, and the mmCIF working group are working to improve structure factor data so it's in an mmCIF format, so that it is more computer readable, it is extensible, and we can add this metadata to that file so you don't have to remember it. It comes straight from your beamline. So that was just deposition. What do we do as curators after that point? We do sequence annotation, ligand annotation, and assembly are the big three that we do. Sequence annotation, we take your sequences and we map them to external resources so that we can tell where things differ. So we can annotate expression tags, mutations, insertions, deletions. Again, this is a controlled enumeration. We have this controlled so that you can't say, this is my favorite mutation, which some people do want to do. We take the protein name from UniProts. Again, quite a lot of you complain that we do that. Why do we do that? Especially that second bit. How many different ways can you write tRNA? It has 4 letters. Apparently, 609 entries have 303 different ways of writing tRNA. Yeah? So this is why we standardize things. So whenever you complain that we take your protein name from UniProt, it's for this reason. It's so that other people can find them. So that when you search in it on our websites, you can find these things. Ligand annotation. We've done some improvements here which would help you, especially for the poorer geometry ligands that we don't get as frequently, but we do get occasionally. So we do, as part of curation, standardize all of the atom names to our dictionary so that people can find them, so you can find interactions. We check the geometry using Mogul. So part of CCD, we have an agreement with them and we check that as part of the validation reports. We have changed how we've done deposition. It has been mentioned that CIF is only allowed now for X-ray entries, and this will come for NMR and EM soonish. Can't tell you when, but it will come. And it does help things. So in PDB, if you upload a PDB file, we just have to graph match. So we take your coordinates and we match it against what is in the CCD. If you give us a CIF, the lovely developers who write out CIF from the major refinement packages have given us the bond order of your restraints directly within the CIF file. And we read that. And we use that to do the match. So it doesn't matter how bad your coordinates are anymore. We do a better match with this. And this is a first step that we have in improving how we validate ligands before you hit the submit button for deposition. We also annotate assemblies. So we take your AU and we expand it. We do this using PISA and discussion with the depositors. And the aim is to have one assembly type per PDB entry. So you have hemoglobin, it should be a tetramer, things like that. We don't have all of the smaller ones, and that's the aim. But what we don't annotate is the biological context of this. So that takes me back to where I started and where we're going next. You may have seen that these things link up. So I've shown you how we do proteins, and that was matching the sequence, the name, matching to external databases. We can build pages for them. Ligand binding sites, I'll show you. Complexes, we're looking at adding some context to things, so you can find things by looking for the complex name. And we're working with resources to do that. As far as ligand pages go, help us design them, please. We're redesigning what we have. I have a lunchtime bite shortly. Please do come along. We'd love your feedback. I've asked a few of you, but I couldn't get round all of you at dinner. That was a bit hard. So we'd love some feedback on here. Help us redesign what we're doing and tell us what you would like to see in here So we redesigned this page to have lots of lovely images, how many structures it's in, and then we can do fragment, we can do similar ligands which have the same different stereoisomers. We can do scaffold analysis of ligands to find similar ligands. And then we can do things like this. It may look a bit confusing. We'll come and hopefully explain this, and you can build on this. Sort of what interacts with your ligand. Because we've standardized everything in the CCD, we can tell you what are all the atoms interacting with across the whole archive. So please do come along and help us. And with that, I will say thank you for listening. Obviously, this isn't possible without being part of the wwPDB, which we partly represent here. We are PDB-E, and of course, the big one here at the bottom. Thank you guys, for providing us the data in doing all this. There's the support of our funders. And one final advert as I finish. If you want to come and look at the data that we have within PDB-E and PDB-KB, this extra annotation, we're holding a workshop in February, and for more information, that website, and do come along and learn what we have. And thank you very much for your attention.
Thank you very much, John. Are there any questions now? There's one right here. Okay.
Hi. Thank you for the nice talk. I was wondering whether you have any tool available now to transform PDBs into CIF files, because there are still many programs that do not write out PDB files, and also if, for example, not only from PDB, but also for example, from Hybrid 36, like other formats that allow have models that are larger than the amount allowed by the PDB.
Okay, the larger format, no, I don't have. Actually, I think Phoenix has a tool for doing that. But for us, when you go to our deposition pages, we recommend PDB extract for doing this conversion if you haven't done it directly within your refinement package. The best answer is to use your refinement program to do that. And there are tools like Gemi as well that will do this for you. But we don't maintain the others. We do maintain PDB extract.
Thank you. Are there any more? One.
John, there's a general comment and question. There's been a long-standing problem of how do we encode in coordinate sets the various levels of disorder and partial order, ranging from things that are absolutely ordered with B factors through things where we know a chain goes vaguely through this area, but we're not quite sure how it gets there, and to completely missing. And we know that, that disordered regions can be functionally very important. And I don't know the answer to this question, and it applies to EM just as much as crystallography. But do you have any comments on that?
So that there are extensions to the mmCIF dictionary that have tried to address this. So there's a service of PDB dev that has an extension to the dictionary that allows more hybrid methods to be described. So they're not at purely atomic level. So you can define a blob, a big sphere. So this blob is that protein. So you allowed the bead sort of representations, and it can handle things like amber and long range restraints being defined in there. So there have been some attempts there at doing that. Again, if this would be a community-driven thing that would come here, and this is via the mmCIF working group. Basically, you guys tell us what you need, and if we don't already support it, we work with you to support it within CIF.